Hello class. So we are going to be covering chapter 17, which is introducing the concept of aromatic compounds. And so that's what we're going to be talking about. So let's take a look at some introduction slides here. So what we have is aromatic compounds. We have something called benzene. We've seen that before in Orgo 1. Now benzene is an aromatic compound. Okay? And there's other benzene derivatives such as toluene and xylene, which are also aromatic. Now, aromatic compounds, they have 4 general features that we need to keep in mind, and these 4 features determine if a compound is aromatic or not. Okay, so we have aromatic compounds. And with an aromatic compound, you're going to look for 4 things. The first thing is that it needs to be cyclic. You can see right on the screen that benzene is a ring. That's a cyclic ring. The second thing that you need to look for is it planar? In other words, is it flat? And one way to do that is look at the hybridization states of the atoms. Are the atoms sp2 hybridized? If they're sp2 hybridized, they're going to be planar. The third thing that we need to look at is, do you have conjugated p orbitals? Now, when you look at benzene, we're going to look at a picture momentarily to see that it has conjugated p orbitals. And the quick way to look at that is when you look at benzene, okay, the quick and easy way to know if a cyclic compound has conjugated pi orbitals or p orbitals is you're looking for conjugation. That is where you have a double, single, double, and it alternates. So that right there is a conjugated molecule. If I draw this molecule right here, that is conjugated as well because you have double, single, double, single. But this molecule right here is not cyclic. So we're looking at cyclic, planar, conjugated p orbitals. Okay. Now the fourth, let's erase this here. The fourth thing that you need to look at is the amount of pi electrons. Of pi electrons has to equal this formula, 4n plus 2. 4n plus 2 is the amount of electrons. So what we do to satisfy this fourth requirement is when we look at our molecule, let me draw benzene again. So when you look at your molecule, you want to count how many pi electrons there are. And pi electrons are in double bonds and triple bonds. And so since I see that we have 3 double bonds here, that translates to this. Every double bond has 2 electrons in it. Not there, that's not right. Right there. So every double bond is going to have 2 electrons in it. So we can see that there's 2, 4, 6 pi electrons. So we take that equation, 4n plus 2 equals 6. That number 6 is how many pi electrons we have in our molecule. this letter N is a variable. This N is whole numbers. What you do is you have to find a whole number and plug it into N, and if you make this statement true, then it's aromatic. So let's look at a list of whole numbers. 0, 1. And I'm going off the board here, so let's come back up here, okay? So if we look at 0, 1, 2, 3, and you keep going on and on. Let's make this, see which whole number can make this statement true. So if I plug in 0, what do I get on the left side? So 4 times 0 is 0, plus 2 is 2. Does 2 equal 6? No, that's not a true statement. So now let's plug in number 1. 4 times 1 plus 2 equals 6. 6 is on the left side, 6 is on the right side. So we have found an integer, a whole number integer right there, that satisfies this equation. So benzene is in fact aromatic because it satisfies these 4 requirements. Okay? So just remember this N term right here. It is just any integer, whole number integer, right, to make that statement true. So I'm going to pause the video for a moment to clean the board, and then we'll come back. Up to this point, we've been looking at a lot of molecules from orbital 1 and in orbital 2. Now I want to talk about some classes of molecules. We have what we've just learned barely. We have aromatic compounds. That's a class of molecules. We also have something called anti-aromatic compounds. And then we also have a third class, which we can classify as non-aromatic. So aromatic compounds, we've seen some examples of those. Those are shown right there on the screen, benzene and toluene. Some anti-aromatic compounds, cyclobutadiene. That is an aromatic compound. So we have aromatics, so benzene, an anti-aromatic compound, and we're going to talk more about what anti-aromatic compounds look like. And then you have non-aromatics. Those are everything else. So rings are non-aromatic. We could have alkyl chains that are non-aromatic. We could have a conjugated system, but because it's not cyclic, it is not aromatic. So these are a few examples of non-aromatic compounds. So those are the 3 classes of molecules that we need to be aware of. So why are aromatic compounds so important? Why do you need to know about them? For one, you can see in that slide there the red benzene rings. They're in those pharmaceutical drugs, and they're very prevalent. They're all over the place in the pharmaceutical industry. And so those 6 examples right there show you some drugs that are on the market, like Lipitor for high blood pressure, high cholesterol. And the one on the top right there on the image, you can see that that's for high blood pressure. Okay? And you can see those aromatic benzene rings in those molecules. On the biology side of things, you have your DNA. Now take a look at the nitrogenous bases in DNA, so adenosine and cytosine and so forth. You can see that they somewhat resemble benzene, okay? but they have the nitrogen atoms mixed inside of the ring. We will talk about that later on in the chapter, but those bases in our DNA are aromatic. And this is so important because aromatic compounds are very, very stable. That's one of their key features when you compare an aromatic compound to a non-aromatic compound. Aromatic compounds are very stable. They have a hard time reacting. And so that's a good thing for our DNA to have aromatic nitrogenous bases, because we don't want our DNA reacting. Because if our DNA reacts, that causes mutation, causes disease and cancer. So our DNA is aromatic and it's very, very stable. That's a key feature here. To drive that point home about the stability of aromatic compounds, we can take the compound there shown at the top there, our cyclohexene. You see that is a non-aromatic compound. Do you see how it reacts with the bromine in an addition style? That's to be expected. But if you took that and treated it with benzene, nothing happens, because benzene is so stable, it doesn't react. Now, to prove this to you with some experiments, we're going to look at heat of hydrogenation. And so we learned this reaction in Orgo 1. And it's this concept right here, where we're going to take benzene and we want to reduce the 3 double bonds. So we're going to treat it with 3 moles of hydrogen gas. And when we do that, we're going to have a reaction in which we reduce all the double bonds. And so we are going to get getting a little happy there with double bonds. We're going to get cyclohexane. You can see all the double bonds have been reduced. Okay? And this reaction gives off a lot of energy. And the heat of the reaction is going to be 208 kilojoules per mole. Okay, so it gives off a lot of heat. Now, let's compare that to a non-aromatic compound, cyclohexene. And see how much heat is given off there. But in order for us to compare apples to apples, we see in benzene that there are 3 bonds, and here in cyclohexene there's only 1. So in order to make this comparable, we're going to have 3 cyclohexenes. And then we're going to compare, and it's going to give us the same product, right? Cyclohexane. But look at the difference. It gives us a lot more energy. 306. No, actually, it's 360 kilojoules of energy. It's not kilojoules per mole, it's actually just kilojoules. Okay. Let me fix that mistake. So that's how much heat is given off when you compare these 2 reactions. So how does that help us understand the stability between these 2 compounds? Well, let's look at it in an energetic light. Okay? Let's erase this Let's look at it from an energetic perspective. So if we have our y-axis here, and our y-axis is in terms of energy. Okay. So what we have here is, let's look at our benzene. All right, we'll draw our little benzene right here. And when benzene undergoes the reaction, it turns into cyclohexane, right? So I'm going to draw a line here representing the energy. And we just learned that when we take this reaction and we do it, the energy, the heat of reaction is negative 208 kilojoules, right? But let's compare when you do the cyclohexene. It gives off it gives 360 kilojoules of energy. So in order for that to happen, because look, it's going to give us the same product, the cyclohexane, same energy level. But in order for it to give 360 kilojoules of energy, that means it had to start at a higher point. That would be a negative. So this hydrogenation reaction is showing us experimentally that more heat is released with the cyclohexene is because it starts at a higher energy. Whereas benzene, it's at a lower energy. And it's at a lower energy because it's more stable. So in the MO theory, also helps us to understand why benzene is so stable. So I'm going to go and make this slide a little bit bigger. So what you see here is the MO diagrams for the benzene. Now look at that top right figure. Do you see the blue, or on the very top here, we have the red lobes and then the blue lobes on bottom? Well, that is a representation of benzene. And every carbon you see has a p orbital. Okay? And when you look at those atomic orbitals and then convert those to molecular orbitals, you see the image at the very bottom. And what's important to see is that there's 6 pi electrons involved. So each one of those atomic orbitals at the top of the top picture has 1 electron each. Okay. So if you could see benzene right here, each carbon has a p orbital. Okay. Where's my pink pen? And in each of those p orbitals, there's 1 electron each. Whoa. All right. And those 6 p electrons are all at the very bottom of our MO diagram. Do you see the 6 pi electrons represented by the arrows, right? Do you see how they're all in they're all in bonding orbitals? And none of those electrons are in anti-bonding orbitals. And because of that, it is very stable. The moment you start introducing the electrons into the antibonding molecular orbitals, the stability of your molecule gets worse. So let me shrink this slide back down. Now we're going to talk a little bit about nomenclature, on how to name these benzene derivatives, okay? When you have a benzene molecule with one substituent on it, it's called the monosubstituent derivatives. You just find the substituent and name it. So when you look at chlorobenzene, what do you see? You see a chlorine attached to the benzene. And chlorines, we know, use the term chloro. So you name it chlorobenzene. You see in the next example, there's a nitro group, so we call it nitrobenzene. When there's an ethyl group, we call it ethyl. Pretty simple nomenclature, right? But then there are some monosubstituted benzene molecules, such as toluene. Now, when you look at toluene, you see that there's one substituent and it's a methyl group. So why don't we call it methylbenzene? Well, a lot of history is involved in organic chemistry, and some of these molecules had names before the development of the IUPAC. And so these molecules right here on the screen just need to be memorized, just straight up memorization. So you can see toluene has a methyl group, whereas aniline has a nitrogen. So these are the 8 most common monosubstituted benzene derivatives with their common names. And those are just things that we need to remember. Now, if the substituent is larger than 6 carbons, in the example of 1-phenyl-heptane, you can see that the alkyl chain in black coming off of that benzene ring is 7 carbons, whereas the benzene ring is only 6. And so what you have is you have to find the parent chain. And in this case, because that black carbon chain is larger than the benzene ring, that's going to take the parent name. And when you have an alkyl chain with 7, the parent name is called heptane. And then what is attached to that parent chain? We have the benzene ring. But when the benzene ring isn't the parent name and it's a substituent, we call it a phenyl group. Okay? Now, these phenyl groups can be represented with just a pH. You can see there on the slide. So if we have 7 carbons here, all right, there's our heptane, but we want to attach the benzene here. 1, 2, 3, 4, 5, 6. We've got to add one more. Okay. What's going on here? Let's see here. I could have represented the molecule just like this. Just like that. You could also use the symbol phi to represent that. I've never used this phi symbol in my life, but it is a thing. I will typically use the pH. That's how I like to do it. And you've already learned up to this point, organic chemists tend to be lazy or efficient, however you want to look at it. So drawing a pH is a whole lot easier than drawing a benzene ring over and over again, especially when you see molecules right there in the bottom left corner of the PowerPoint, you have 4 phenyl groups. And so there's just a lot of drawing. Okay? We have a very common molecule called xylene. Xylenes are molecules that have 2 methyl groups attached. So in the PowerPoint slide, you can see that there are 3 molecules there. They're all called xylene because they all have 2 methyl groups as substituents. Now, depending on where that substituent lies, or the 2 substituents are in relationship to one another, you get ortho, meta, and para. Ortho, meta, and para are just words that help us understand the relationship between 2 substituents that are attached to a benzene ring. And so what we can look at is generically, if you have a benzene ring here, and you have a substituent, and the substituent can be anything, and another substituent. Okay? So these 2 substituents, they are separated by 1, 2. When you number the carbons in the benzene ring, you can see that X and Y are in a 1-2 relationship. And when you have that, you have ortho. If you compare, if we put X here and Y there, you can see it's a 1, 2, 3 relationship. And when it's a 1, 2, 3, we have something called meta. And then if we have this and a 1, 2, 3, 4 relationship, we call that para. Now for xylene, you can see that the X and the Y, if the X and the Y are both methyl groups, then they're called xylenes. And you can see that there's orthoxylene, metaxylene, and paraxylene. But now there's more molecules than just xylene, right? So we can have X's and Y's, and we will look at some other molecules with different substituents. But they all have that ortho, meta, para relationship. So if you look at the orthonitroanisole, you can see that the 2 substituents are in a 1-2 relationship, so it's ortho. And then the metabromotoluene, you can see, is in the 1-3 relationship. And then the parachlorobenzaldehyde, you can see, is in the 1-4 relationship. Okay? Now, one thing to notice about these molecules on your screen, do you see how they don't have the name benzene in them? When we come over here, remember those? That has benzene as the parent name. But when you come back here, you see we have anisole and toluene and benzaldehyde. Well, we're using the common names now. So when you see a disubstituted compound, how do you know when to use the parent name benzene versus the common name? And I want to show you a trick that I use to help keep that straight. Okay? So let's take a look at the orthonitroanisole. Okay, so let's draw that. Two. When you have a disubstituted benzene and you're trying to figure out how to name it, I break it up into their monosubstituted versions. So I'm going to take this molecule here and redraw it like this, and just have O like that. And then I'll do it for the nitro group. Okay. Now when I look at these two right here, which one has a common name? This guy right here is called anisole, and this guy is nitrobenzene. So if you have two molecules here and one has a common name, you go with the common name. So this molecule right here has a common name because of this substituent right here. That's an anisole substituent. And so the whole molecule is, the parent name is going to be that common name. And so you see the other examples right there in the slide. All right. So let's see here. So what I'm going to do is I'm going to finish the nomenclature section, and then I'm going to go back to something that we need to talk about. Okay? I missed something. Okay, steps for naming the compounds. Well, you need to identify the parent. Is it a benzene? Is it a common name? You find the parent. You identify the substituents. And then you need to number the substituents. The steps for naming here are when you're looking at benzene derivatives with more than 2 substituents. So typically 3 or more substituents. How do you name benzene derivatives that look like that? And that's what these steps right here in this slide are showing us. Okay? So it's just easier for me to just show you an example instead of just reading these bullet points for you. So let's look at an example, okay? So there's our molecule. How do we name it? Well, when we look at that molecule, are we going to name it a benzene or a phenol or a common name? And when we look really, really carefully, you see the molecule is in red. It is a phenol because of that hydroxyl group, the OH. When you have an OH on a benzene ring, the common name for that molecule, shown here, that is a phenol. And then attached to that phenol, you see 2 different substituents, the bromine. Okay. Let's put it right there. Okay. So we've identified that there is a common name for this molecule. So the parent name is our phenol. Okay? That's our step 1. Step 2 is to name the substituents. And we see that there are 2 bromines. So we say, hey, there's a bromo attached. Those are our substituents. And there's 2 of them. All right. Step 3, we need to number these. Number the carbons. Now, when you have a common name, like phenol, the substituent that gives the benzene derivative its common name is always going to be labeled or numbered 1. So we can see that this OH is the substituent that gives it the parent name of phenol. So that means this carbon has to be carbon 1. And then you go around the ring to make sure you give the other substituents the lowest locator number possible. So we now see that our two substituents, the bromines, are located at carbon 3. So we can say 3-bromo and 5-bromo. That's where they're located. All right. And now you just put it all together. We have to put the bromos first. And the way, since there's 2 of them, we have to go 3, 5. That's telling us the location of the bromine. And then whenever you have numbers and letters, you have to separate them by a dash. And there's 2 bromines. And so we have to use the prefix di to represent that there's 2 bromines there. And then we say, hey, what are the substituents? They're bromines, so dibromo. And then we add the parent name. So this compound is called 3,5-dibromophenol. Right? Now, what if I change this up a bit? Okay? What if I took off the hydroxyl group? Took off the hydroxyl group and then put on an ethyl group. Now what is the name of this compound? Okay. So what's the first thing that we need to do? We need to name the parent. We look at this molecule. Do bromines, or does one bromine give us a common name? Go back to that list of the 8 common names, and you'll see that there's not. What if we have an ethyl group? Is there a common name for an ethyl? And there's not. So when we look at our molecule, there's no substituents that gives this molecule a common name. So then that would mean that the parent name is going to be benzene. So that would be step 1, naming the parent name, right? The second step would be to name the substituents. We have the bromos, great, okay? But now we have another one, we have our ethyl group. 2 carbons is an ethyl group. Now we have all of that. The next step, or the third step, is we have to number the substituents. So let's get rid of these right here. Now class, I'm going to draw 3 versions of this molecule here. Or I'm going to draw this molecule 3 times, but numbered a little bit differently. And I want you guys to think to yourselves and tell yourselves which molecule is numbered correctly. Okay. So I'm going to draw 3 versions here. All right. So let's number these. 1, 2. We have that option. That one. Between those 3 options, which one do you think is the correct way to number this benzene derivative? Now, I would highly recommend that you just pause for a moment and think about it. All right. Now the answer right there is in number 3 there. It says number the parent chain and assign the locant to each substituent. Now, we have to do that though in priority. So the trick here is we have to prioritize the numbering scheme based off of alphabetical order. So when I look at my substituents, I clearly see B comes before E. So the bromines have to have the smaller locator number. So I see this one in the middle, the ethyl group has locator number 1. So that one's no good. Okay. This one has a locator number. This bromine has a locator number of 1. But this one, bromine on the other side right here, has a locator number of 5. And the ethyl is a 3. Well, why is the ethyl getting a lower number, locator number, than the bromine? That's not fair because the rule is it has to be alphabetical. So when you look at this, you can see that the substituents that start with B has the smallest locator number possible. And then the ethyl group has 5. So this molecule on the far left is the correct way to number it because it's going in alphabetical order. And so now that they're named properly, we can add the location number in the substituents. So that's a 1, that's a 3, and that's a 5. And now you just put it all together in alphabetical order. So we have 1,3 dibromo. We're adding another number because we need to tell us where the ethyl group is. Ethyl. And then what's the parent name? Benzene. So that's how you would name that molecule. All right? How much time do we have here? Okay, we have 8 minutes. So I'm going to go back to take you here, okay? Understanding MO a little bit more. Okay? Now I want to take a look at benzene and remind you how to look at hybridization states. Okay? So if we just have a molecule like this, like that, so that this is a hydrogen right here. What is the hybridization state of that carbon right there? How do you figure it out? Recall that when you're looking at this carbon right there, you just count how many electron groups there are attached to that carbon. So we have this electron group, that one, and that one. So there's 4 electron groups. And when you have 4 electron groups, that means it is sp3 hybridized. Now, when you look at a molecule with a double bond, and you have a hydrogen here, what is the hybridization state of that carbon? We just look at how many electron groups are attached to that carbon. There's 1 group, 2 group, 3 groups. So there's 3 electron groups, and you can see how I took the alkene, the double bond. I just said that's 1 electron group. And that's going to give us our sp2 hybridized. And then if you have a alkyne like that, and we're going to ask what is the hybridization state of, let's say, that carbon right there, you can see that carbon right here is directly attached to that electron group and that one. So there's 2 electron groups, and that's going to be our sp. Now our focus in this chapter is being able to identify sp2 hybridized carbons. Okay. Now when we look at benzene, what is the hybridization state of all the carbons around benzene? Well, don't forget, let's do this carbon right here. How many electron groups are around this carbon right here? Okay. How many electron groups are around that carbon that I just circled in pink? There's 1, 2, 3. So there's 3 electron groups, so that makes it sp2. Okay. Now what does that actually mean when we say it's sp2 hybridized? So recall, when you look at the valence electrons for carbon, you have an electron configuration that looks like this. You have a 2s orbital, and then you have your 2 p's. And there are 4 valence electrons for carbon, so the electron configuration would look like that. But when you look at that electron configuration, you only have 2 electrons that are able to form, or you only have 2 orbitals that are able to form bonds. But carbon forms 4 bonds. And so this electron configuration does not explain why carbon forms 4 bonds. Do you remember how in general chemistry and in Orbital 1, you talked about hybridization? And when we hybridize that, what we're going to get is we're going to take these orbitals, the 2s's and the 2 p's, and hybridize them into an sp2 and a rp. So what's happening here is we are taking 1 s orbital and 2 p orbitals and hybridizing them to be at the same energy. So that's what sp2 stands for. This s says we're grabbing this s orbital, and 2p, so we're grabbing these 2 right here to form 3 orbitals of the same energy. Note that we did not touch that one. So that one just stayed over there. And to be consistent, we could call that our 2p. And so now we have a hybridized, and now the 4 valence electrons go like that. And now we are able to form 4 bonds looking at that electron configuration now. Now what that does here is a carbon atom, okay, that is sp2 hybridized is going to have 3 sp2 hybridized orbitals. And they are going to be in the same plane. So these are our sp2s. They are in the same plane. But then we still have this orbital right here, the p orbital. The p orbital is going to be perpendicular to this plane. And so what that means is that the p orbital is going to be coming off of this carbon, it's going to be coming out of the board, and the other lobe is going to be going into the board. And so what we do is if I take this carbon right here and flip it like this, you will see that the p orbital will be above and below my hand. So when we take a look at benzene, what you're observing is that this bond right here, all right? So let's try to color or highlight this. This bond right here is using an sp2 orbital to form that bond. And then this bond right here, okay, is using another sp2 hybridized orbital. And then there's this hydrogen atom attached. And so that bond right there is being formed by another sp2 hybridized orbital. But what about the pi bond? This guy right here. That is formed from the p orbitals that are perpendicular. And so if we take a look at a benzene ring and then look at it in this structure right here, so let's focus our attention on this carbon. This bond, and that bond is these three right there. And then in orange, there's our p orbital. And so when we're looking at this carbon right here and this carbon right here, forming, so this pi bond right here, so it'd be this carbon and that carbon. All right. How is that pi bond being formed? Well, it's because there's an electron there and an electron there. And those two right there is forming that double bond. And so it's very important to be able to see that these lone pair, or these electrons are in p orbitals. So if I look at this carbon right here, do you see how this electron right there is that guy right there? And so understanding the hybridization state is going to help us understand aromaticity and being able to predict aromaticity. So I am out of time, and so we will pick up where we left off right after nomenclature in the next video.